So in today's class, we'll continue talking about the different types of time response specifications which are there. These time response specifications, as we have already mentioned in the last class, that they are mainly important from the design point of view. From the design point of view means that whenever you are, suppose let's say that you are a designer and you want to design a control system and you want to set the parameters of the control system in such a way that certain specifications in the output are met. Certain specifications can be, let's say your system might have might be tolerant to a specific amount of that peak overshoot, or your system, you need your system to settle down or reach the steady state very fast. So in those cases, these kind of this like peak overshoot, settling time, rise time, peak time, all these kinds of parameters will be specified to you, and you have to design or you have to select the parameters of your control system in a way such that those kind of specifications are met. Okay, so then we started talking about the steady state errors. So basically this steady state error, so it is basically the measure of like how much accurate the system is, and when you are providing an input to that control system, what is the difference between the steady state output as well as the specific input that you are providing to the system. So the difference between the actual output to the desired output, that is at t equals to infinity, when the system is reaching a steady state, that is known as a steady state error. Okay, so related to the steady state error also, we can calculate different kinds of error constants, and these constants will also will give you an idea about how your system is performing for a specific kind of input that you are providing. So this we already talked about. So this is like if you want to write the expression for the steady state error. So the steady state error, you can write it either as like limit t tends to infinity e of t, or you can use the final value theorem and you can write this in case if you don't know the exact time domain expression for this error, then you can use the Laplace transform of that expression and you can find the steady state error as limit s tends to 0 s into es. Now there are like three different types of static error constants. Okay, so the static error constants, basically they are, so when suppose you are provided with a system, so this is a closed loop system, unity feedback closed loop system which is provided to you. So here you see that if you want to write the expression for the steady state error, that you can write that ESS will be equals to limit s tends to 0 s into RS is your input, RS by 1 plus GS, right? So this is your expression for us for the steady state error if you are given a system like this. Now let us say that the input that you are providing, that is the value of RS that you are giving to the system, that is a unit step input. So in case of an unit step input, the value of RS will be equals to 1 by S. So you can substitute that in the expression for E of the steady state error and you will end up with an expression like this. So ESS for a step input or a unit step input will be given by 1 plus limit s tends to 0 GS. Now this expression, this limit s tends to 0 GS, this is known as a position error constant. And you can see that you can express ESS, so you can write ESS will be equals to 1 by 1 plus Kp. Now the aim or the goal for a good design would be that we should always try to minimize the steady state error. The steady state error should be as low as possible. So in order to make this steady state error very less, we would need that the value of Kp should be, in this case, the value of Kp should be as large as possible. So if the value of Kp is ideally, let's say if the value of Kp is infinite, then the steady state error will be equals to 0. So from the design point of view, if you want to keep the steady state error to be very low, you would need that the steady state error constant should be very high or should be as high as possible. Similarly, when you are providing a ramp input to your system, so in case of a ramp input, you have RS will be equals to 1 by S square, and similarly if you write the expression, so here RS will be substituted by 1 by S square, S and S one s gets cancelled out and there will be another s in the denominator. So it can be written as limit s tends to 0, 1 by s plus s into gs. This can be again said that you can make this s value as 0 and this will be 1 by limit s tends to 0 s of gs. And this expression limit s tends to 0 s of gs, this is known as the velocity error constant. And when you are providing and here you see that in terms of the velocity error constant, the steady state error is just inversely proportional to the velocity error constant. And similarly, when you have a parabolic input, you can find that the steady state error will be equals to 1 by limit s tends to 0 s square gs, and this is known as the acceleration error constant. So we have three static error constants. One is the position error constant, which is the error constant that you are getting when you are exciting the system with a step input. Then you have a velocity error constant. In velocity error constant, you are exciting the system with a ramp input. And in case of an acceleration error constant, the input that you are providing to the system is of parabolic in nature. Okay, so now let's see like what are the implications of these error constants in a system. So suppose let's say that you have a transfer function and you can express the transfer function in a factor or in a pole zero kind of an form, which is given by this. Okay, so you can either express a transfer function in form of a time constant form, or you can express it in a pole zero kind of an expression. So here we are talking about the pole zero kind of an expression, where in the numerator you have some constant and multiplication of like all the zeros that are there in the system, and in the denominator you have all the poles that are present in the system. Now here if you see that in the denominator you have a term s to the power n. Okay, so that means there are n number of poles at s equals to 0. So at origin you have n number of poles. Okay, so if you want to see what is the type of the system, so the order of a system is what is the maximum power of s that is there in the denominator of the system. So if you have a system where the denominator, the maximum power of the denominator is h to the power 4, then you will say this is a fourth order system. But order of a system and type of a system, they are not same. Okay, so the type of a system that is governed by the term s to the power n. So it depends on if you have like n number of poles at origin, then the type of that system is equals to n. So that is called as a type n system. And n number of poles at origin, that also indicates how many number of integrations are there in the system, because 1 by s is equivalent to a block whose transfer function is basically an integration. So you can say that if you have n number s to the power n in your denominator, that means n number of integrations will be there somewhere or the other along the block diagram or in the system. And when s tends to 0, this s to the power n, this term, so when s tends to 0, these terms will become just constants p1, p2 and till pn. But this s to the power n term, that actually dominates in determining what will be the steady state error. Now let's see like how it affects the steady state error. So suppose you are given with a type 0 system. So type 0 system means in the denominator the power of s is 0. So you have sort of s to the power 0 over here. So s to the power 0 is 1. Okay. So in case of a type 0 system, you can write that the expression for this position error constant, or if you write the expression for the steady state error in terms of position error constant, so ESS was equals to 1 by 1 plus Kp, right? And here if you see the value of Kp, so Kp is nothing but, so Kp is equals to limit s tends to 0 s into gs. No, limit s tends to 0 only gs. Sorry, this is kb. Yeah. So you have okay. So here you see that you can just write that the expression for the steady state error will be equals to 1 by 1 plus kp, which is a constant because the value of g0 is a constant value. So g0 will be equals to k dash multiplied by z1 z2 till zm, then divided by p1 p2 dot 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 till pn. So this value of kp is a constant. So that means the steady state error will be some constant value. Now if you want to find out what is the velocity error constant, so you see that in case of velocity error constant, so velocity error constant kv is given by limit s tends to 0 s into gs. So now if you see that if you make limit s tends to 0 s into gs, so then the value of kv is equals to 0 for this type 0 system. So you just simply write s into gs, so you have s in the numerator, and if you write so for the limit s tends to 0, this value will become equals to 0, and this ess will be equals to 1 by kv. So 1 by 0 will be, that means you will have infinite steady state error when you have a ramp input provided to this type 0 system. Similarly, if you want to find out for the parabolic input, in case of a parabolic input also, this kp will be equals to limit s tends to 0 s square gs. Similarly, this value is also for this type 0 system, limit s tends to 0 s square gs is also equals to 0. So that means the value of ess, which is equals to 1 by ka, this will also be equals to infinite. That means you can say that if you have a type 0 system, then it provides you with a constant position error, and but there is infinite velocity and acceleration error at steady state. So if you see the expression, or if you see the plots for this system, so this is a type 0 system we have. So if you have a step input, and this is how the input or the output is actually changing with time. So in this case, you see that for a step input, there will be a finite steady state error, and that value will be given by 1 by 1 plus kp. In case of a ramp input, the steady state error will keep on increasing at t equals to infinity, there will be infinite steady state error, because see the input and output, they are actually diverging from each other. So with time, the error or the difference between the input and the output, that is increasing. So that means at t equals to infinity, the steady state error will be infinity. Similarly, in case of a parabolic input also, the output is not following the parabolic input properly. It is sort of diverging away from the input. So that means the steady state error will be equals to infinity. So if you have, so when you are designing a system, you will be given with a specific value of kp, kv and ka. So this will be ka. For a type 0 system, you will have constant position error and infinite velocity and acceleration error at steady state. Now, if you have a type 1 system, okay, so type 1 system means in the denominator you will have s multiplied by, so there will be s to the power 1 in the denominator. Now similarly, if you want to find out what is the value of the steady state error at for a step input, so then the value of ess will be, so here you see that if you have this type 1 kind of a system, so in case of type 1 system, so ess is given by 1 by 1 plus kp. Okay, so 1 by 1 plus kp, kp is nothing but g of 0. So g of 0, you see g of 0 is equals to infinite. So kp is equals to infinite. So if kp is infinite, then your steady state error becomes equals to 0. Right. Similarly, if you have, if you see the velocity error constant, if velocity error constant is given by kv, then the steady state error ess will be equals to, so this will be equals to 1 by 1, this will be equals to limit s tends to 0, 1 by s into gs. Now limit s tends to 0, s into gs, that will be some constant finite value, because you have s over here, and at s tends to 0 you will get a constant value. So that means for a ramp input, if you provide a ramp input to a type 1 system, then the steady state error will be a constant value, and that steady state error will be governed by the velocity error constant. And if you want to see that the steady state error for a parabolic input, in case of parabolic input also, we will see that the ESS value is equals to limit s tends to 0, 1 by s square gs. And this value, limit s tends to 0, s square gs, this is actually equals to 0. So that means you will have infinite steady state error when you are providing a parabolic input. So in conclusion, you can say that if you have a type 1 system, then the position error or the steady state, you have 0 position error, you have a constant velocity error, and you have infinite acceleration error at steady state. So these are the graphs. So you can see that for a step input, the steady state, the output actually reaches the steady state and it follows the input, and the steady state error is 0. In case of a ramp input, the output follows the ramp input with a constant error which is maintained at 1 by kV. And for parabolic input, similarly, the output actually diverges away, and then the steady state error will be equals to infinite. If you have a type 2 system, so type 2 system means the value of s will be, there will be an s square term in the denominator. So similarly, you can see that for this s square term, this ESS value for this position position error will be equals to 0. Similarly, ESS for this velocity error, that will also be equals to 0, and the steady state error for an acceleration or for a parabolic input, that will be a constant which is given by 1 by Ka. Right? So you can say that for the type 2 system, you have 0 position error, 0 velocity error, and a constant acceleration error at steady state. So if you see that as we are increasing the type of the system, that means as we are increasing the number of poles that are present at origin, you see that the errors that are present in the system for various kinds of input, they are actually the steady state errors, they are actually getting nullified. So in the first case, when we were talking about this type 0 system, you had constant position error, and these velocity and acceleration error were infinite. For type 1 system, the position error became equals to 0. The velocity error now reduced from infinity to some constant value. Acceleration error was still infinity. Then for type 2 system, you have 0 position error, velocity error, but the acceleration error is some constant value. So you can say that as the type of the system is increasing, the more number of errors or steady state errors can be nullified when you are dealing with a system of a higher type. So this error constants, this velocity, position, velocity, and acceleration error constants, they actually describe the ability of the system to reduce or to eliminate the steady state errors. So to eliminate the steady state errors means that how accurately the system is able to track the input that you are providing. So you can say that if you have a very high value of the static error constant, then the steady state error will be low. Also, if the type of the system increase, this I have already told, as the type of the open loop system increases, more steady state errors are eliminated progressively. So you can say that if you know the value of this Kp, Kv, and Ka, so depending on that, those values, you can find out what will be the final steady state error of your system, provided you know what is the kind of input that is being there, that is being excited, used to excite the system. Now, the steady state error, there are actually some disadvantage also of steady state error. Disadvantage in the sense, like they do not provide any information about how the steady state errors. So we know that we have, like, since we have only 3 steady state error constants like Kp, Kv, and Ka. So one is for step input, one is for ramp input, another one is for parabolic input. But if you have a system if the input to your system is something other than these three kinds of inputs, if you have something else, then the steady state errors will not be able to provide the information about this Kp, Kv and Ka. They won't be able to provide information about the steady state errors. Also, it does not say or it does not indicate that how the error function is actually changing with time. So it does not provide you with any information about how the error signal is changing, like in the transient phase, how that error is changing. It only gives you the information about what is happening at the steady state, or what is the error which is happening when you have reached the steady state. But then again, you need these values because you need to minimize the, obviously, whenever you are designing a system, the main aim should be, one of the main aims should be that the steady state error should be as low as possible. So these are the types of steady state errors, which are steady state error or the steady state error constants that are present in different kinds of system. Okay, so now we'll see that what will be the effect of like, let's say you have a system, you have a second order system. Okay, so this second order system, the general form of a closed loop second order system is given by omega n square divided by s square plus 2 zeta omega ns plus omega n square. Now let's say that if we add a 0 to the system. Okay, so we are adding, let's say we are adding a 0 at s equals to minus z. So that means in the numerator term, there will be this s plus z that will come in the numerator term. And we are actually modifying the numerator, the gain of the numerator in such a way that the steady state gain of or the initial gain for both the systems remains the same. Okay, so here also if you see the value of C by R into at 0 is equal, so the steady state will be equals to 1. Okay, and here also when we are providing, we are adding a 0 to the system. So in the numerator you have s plus z multiplied by, initially there was omega n square, so we are adding one more 1 by z term over here, so that the steady state gain, that is Cz by R at 0, will be equal to 1. Now if you see that for a unit step input, the steady state output for this system is equals to 1, right? So that means the system will be able to track the input with 0 steady state error. So if you want to write the function of this, so if you want to write the expression for Cz of s from this equation, so you can write Cz of s will be equals to, so here, so this term is nothing but Cs. So when you have a step, when you are providing with a step input, so you have Cz will be equals to, this term will come or will contribute to the value of Cs, which you can find over here. So this is for Cs, and the second term, which is equals to, that will be equals to 1 by z multiplied by s into Cs. So you can write Cz of s is equals to Cs plus 1 by z into SCS, right? So from here, if you take the Laplace inverse, so you can write the time domain expression. So Cz of t will be equals to Ct plus 1 by z multiplied by derivative of Ct, right? So this is the, so, and the expression for Ct is something like this. So if you take the derivative of this expression, divide it with z and then add it with the original expression, then you will get what the expression for Cz. Now let's see what is the, so if you see this plot, so in this plot basically this is a graph for when your system, the system that we just had, so this is the second order system. So this second order system is now excited with a unit step input. So for a unit step input, if there is no 0 in the system, so then the output follows a curve like this. Okay, so this one, and when you add a 0 to your system, and then similarly if you calculate the steady state, rather the step input or the step response, then you will see that when you are adding a 0 to your system, then you see that there is a pronounced peak. So initially for the previous system, the peak was, let's say, some value x. If the value of the peak was some value x, but the moment you are adding a 0 to your system, you see that the system, the peak or the maximum overshoot that is present in the system, that is actually increasing. So two phenomena are there. So one, the maximum value of the peak or the peak overshoot that increases, and also you see that this peak is coming at an earlier stage. So before if there is no 0 in the system, so let's say you're getting the peak at T1, but the moment you add a 0 to your system, you are getting the peak earlier, where T2 is less than T1. So you can say that the effect of adding a 0 to a system, that is reflected as a significant early peak in the system response, as well as an increased peak overshoot. So now if the value of this Z, or the 0 that you are adding to your system, if you add the 0 closer to the origin, in that case what will happen, this peaking phenomena, or this the rise in the peak overshoot, that phenomena, that will be more pronounced. So ideally we would not want a 0 to be present very close to the on the real axis. We don't want the 0 to be very close to the origin, because that will result in a very high peak overshoot in the system, and the system might not be able to sustain that kind of an overshoot. But if you increase the value of Z, so that means if you move the 0 farther into the left half of the S-plane, so then what will happen is that this effect, this peaking effect, that will become less pronounced. And if you place a 0 which is very far away from the origin, in that case, that effect of the 0 on the transient response of the system, that can be neglected. So it is sort of, you can say that if you have a 0 which is far away from the origin, the effect of that 0 on the transient response, that is negligible. Okay. So clear till now?
Yes, ma'am.
Okay. So now, let's try to solve, or rather I would want you to solve this problem. So here, let's say that you have been given with you have been said that the open loop transfer function of a unity feedback system is GS. So this open loop transfer function is given. Now you have some specifications are provided that the system should meet the following specifications, like the peak time should be equals to 1 second. This peak overshoot will be equals to 10%. Okay. So now what you have to do is that you have to find out whether there is any value of this gain K such that both these conditions are satisfied. And if you don't, if there doesn't exist a value of K for which both these conditions are satisfied, then what you have to find out is that you have to find the value of K such that both the values of this peak time as well as the peak overshoot, they are violated or they are exceeded or they are less by the same percentage. That is the second question. And the third one is if you have an adjustable pole. So if this pole, that pole at S plus 2, S equals to minus 2 is adjustable, you can change the position of the pole. Let's say that that position is S equals to minus alpha. Then what will be the value of this? So you have to find out what is the value of the K and alpha in order to meet the given two specifications. So in order to find that, first of all, what you need to do is that since you have been given, so this value of TP is equals to 1 second that is provided. So we already know that for a second, so this will be, so if you write the closed loop transfer function of the system, so this is a second order system. So and we already know the expression for this TP for a second order system, right? So from that expression, so you have to find out what will be the value of, so if you remember the expression for TP was something like, yeah, so TP was pi by omega d. So you can write this is equals to pi by omega n square root of 1 minus zeta square. Okay, so yeah, so you have a pi by 1 minus zeta square. So you can find out from here you have one expression. So there is zeta and there is omega n. Similarly, for this MP equals to 100%. So you can write the expression for MP. MP's expression was like 100 into e to the power minus pi zeta by square root of 1 minus zeta square. So from here you can put the expression for this the value, and you can find out what will be the value of zeta. So once you find the value of zeta, then you can find out what will be the value of this k in order to satisfy this equation, this parameter. So how will you find that? Because if you have been given like gs into hs is equals to k by s into s plus 2. So if you write the characteristic equation will be 1 plus gs hs will be equals to 0. So that means this is s into s plus 2 plus k is equals to 0. And when you have this in general, you can write. So this is the general expression for characteristic equation of a so this is the general expression for the characteristic equation of a second order system. So now what you can do is that you can compare this equation with this, and then you can find out what will be the corresponding values of zeta and omega n. So then if you know these, then you can find out what will be the value of k, and then you see whether this k is actually matching with the k value that you are getting when you have TP equals to 1 second, and the k value that you are getting when the value of MP is equals to 10%, whether those two k's are matching or not. So if they are not matching, then you have to find out what is the, then you see that it is given that it will be varied by the same percentage. So then you can assume that, let's say, TP will be equals to 1 into some 1 plus x. So let's say that it is getting changed by x percentage, and similarly MP will be equals to MP dashed will be equals to MP into 1 plus x. And once you have this, then similarly again you will have to do the same kind of calculations, and you have to find out what will be the value of k and x. Okay, so you try to solve this problem at home, and in case if you find any difficulty, we'll discuss this in tomorrow's class. Okay, so now we'll move on to the concept of stability. So the stability, actually we have already talked about stability earlier, so I'll not go into more details about these things. So stability means that if the system comes to the equilibrium state, so that is whenever it is to an equilibrium state, whenever it is subjected to any kind of initial condition, that is known as a stable system. So that means if you have a bounded input to your system, then the output that you will be getting, that will also be a bounded output. So if you have that kind of a system, then it is known as a stable system. Now if you have, for a bounded input, if you have an unbounded output, that means that output is going to infinity with time, then you will have an unstable system. And when you have a marginally stable system, in case of a marginally stable system, the system is actually oscillating about its equilibrium state, and it is not reaching any kind of a steady state. So these were like 3 kinds of stability you can have. So you can either your system can be stable, it can be unstable, or it can be marginally stable. So these 3 kinds of system you can have. Now then there are like if you want to quantify, or if you want to see what is the extent of stability, so there are 3 parameters. So one is absolute stability. So absolute stability, it says that the condition whether the system is stable or unstable. So it will just give you a qualitative thing saying that it is yes, it is stable, or no, it is not stable. And for relative stability, what is relative stability? So once you have found that your system is stable, so in that case, you might need to know how much of stability or the degree of stability of the system is there. So that means if you have your system and suppose you are changing some parameters in your system. So for some specific parameter value, maybe your system is stable, but for a different value of that parameter, your system might become unstable. So you want to know. So if you want to know what will be the range of that parameters for which the system will remain stable, that is known as this relative stability. Okay. So similarly, conditional stability is also something that is the range of the component values for which you have the stable system. Now these we have already discussed, so I'll not go into. So just one thing. So if you have a system which is bounded input stable, so that means that the impulse response should be absolutely integrable. Okay, so if the impulse response of your BIBO system is absolutely integrable, then you can say that the system is stable. If you want to see the stability in frequency domain, so in a general, if you write the general expression for a transfer function in a polynomial form, so let's say that you can express this GS in terms of a numerator polynomial divided by a denominator polynomial. And this denominator polynomial is basically the characteristic equation of the system. So you can write that ds will be equals to 0. Now the roots, if you find out the roots of this characteristic equation, so you can say that the roots of this characteristic equation, they are basically the poles of this system GS. Now let's assume that these poles, they are distinct, and they are distinct means we can express this transfer function in a form like in a partial fraction form. So that means we can write it in terms of a1 by s minus s1 plus a2 by s minus s2 till s minus sn. So since there are like the order of the system is n, so that means there will be n number of roots present in the system. So let's say that we can write the expression as in a partial fraction form, which looks like this. So that means the poles of the system are here. The poles of the system will be S1, S2 till Sn. So these are the poles of the system. And these poles, they can be real poles, they can be imaginary poles, they can be complex poles, depending on what are the coefficients that are present in the system. Okay. So now let's say that if your system has real pole. So if you consider this term, so this is, so in general you can write, so this term will be ak by s minus sk. So if the value of this sk is a real value, so let's say this sk is equals to a. So in that case, when you have sk equals to a, so that means the pole will lie on the the pole will lie on the left half of the S-plane. If the value of a is less than 0, the pole will lie on the right half of the S-plane if the value of a is greater than 0, and if the value of a is equals to 0, then the pole will lie at the origin, right? So now if you take the Laplace inverse inverse Laplace of this expression, you will see that the inverse Laplace transform of ak by s minus, now we are substituting sk with a, so ak by s minus a, so that inverse Laplace transform gives ak e to the power at into ut. So this is the, so inverse Laplace transform means, so this is the impulse response. Okay, so this is the impulse response for a system which is whose transfer function is given by this. Now if you draw or if you plot this impulse response, you will see that if the value of a is less than 0, so this exponential term will be a negative exponential, so it will be e to the power minus at into ut. So if the moment you have a negative exponential, so that means the impulse response will slowly die down to 0, and after a finite time the output will become equals to 0, right? So that means that for a bounded input you are getting a an output which is a bounded output, because the output is gradually going down to 0 as t is becoming large. So these are the two. So if the pole, let's say this is the value of A, so one pole lies at here. So these are the two kinds of poles. If the pole position is at this point, so then you will the impulse response will look like this. And if the pole position is lying even farther away from the origin, then you will see that the decay will be much more faster, and it will reach and it will die down and will go to infinity. It will reach 0 at an earlier stage. So that means the slope, or you can say that the slope of decrease or the of this impulse response, that is higher if the pole is lying away from the origin. Now, if the value of A is greater than 0, in that case, so these are the two cases. So in greater than 0 means the poles are lying on the right half of the S plane. So if the pole is lying over here, you see that the impulse response, so it will no longer have a negative exponential, it will have a positive exponential. So it will be e to the power at, and A being positive, this output or this impulse response will keep on increasing with time. So that means at t equals to infinity, the system or the output is not bounded, and it is getting, so you can say that the system is unstable if you have the value of A is greater than 0. Similarly, here also, if you shift the position of the pole to even more towards the right half plane, so the slope, or it will reach infinity, so the slope will be much more higher. Now, in the third case is that if the pole lies at the origin. Okay, so if the pole is lying at the origin, means the pole is lying here. So then you can see that the expression was something like ak e to the power at into ut. So for A equals to 0, you will have just ak into ut. So you will have a constant output which is given by this. So ut is basically the step. So that means, so you will have a constant output. Okay, so having a constant output here, it indicates that obviously if it is constant, so that means the system is not absolutely integrable, because the output is not per se, the output is not bounded. So you can say that even though or you can say that since it is not going to infinity, so it has a finite value, but so you can say that the output is bounded, but still it is not, the system is not absolutely integrable, right? Because it is not going to, the impulse response is not going to 0 at t equals to infinity. So even though for a bounded input you are getting a bounded output, since the system is not absolutely integrable, the system is neither stable nor unstable. This is the condition of the system is that it is marginally stable. So if you have the poles at origin, so that means the system will be, or not only at origin, it depends on if your pole is lying on the imaginary axis, then your output or your system will be marginally stable. Now, if instead of real poles, let's say you have complex poles. Okay, so complex poles mean they always exist in complex conjugate form. Okay, so if you have, let's say let's say the poles are sk equals to a plus minus jb. Okay, so that means you have one complex pole over here, the other complex pole will be somewhere over here. So let's say let's see the impulse response for this complex pole. So if you see that if the value of A is less than 0, so that means the pole will lie on the left half plane, and if the value of A is greater than 0, then the pole will lie on the right half of the S plane. Now you can write the expression for GS will be equals to then AK by S minus A minus JB plus some AK star divided by S minus A plus JB. If you take the Laplace transform of this GS, then you will get that it is expressed as AK e to the power AT cos of BT plus phi. So the moment you have cos of bt plus phi, so that means you can see that there will be some kind of oscillations in the impulse response, right? And since there is an exponential term associated with it, so that means those oscillations which are present, that will be governed by the exponential term. So depending on whether the exponential is a positive exponential or a negative exponential, depending on that, the oscillations will either die down with time or it will keep on increasing with time. Now if you have the value of a less than 0, so that means this exponential will be a negative exponential. So that means the impulse response is absolutely integrable. That means that this oscillations which are present, that will slowly die down and it will reach 0. Okay, so that means that the system will be stable when the value of a is less than 0. But if the value of a is greater than 0, then you see that this is the plot for plot of the impulse response of when the value of a is greater than 0. So for a greater than 0, you see that the impulse response will keep on, these oscillations will keep on increasing and the output will not be bounded. So since the output is not bounded with time, so that means the system will become unstable. Then you have the third case where the value of a is equals to 0. So the value of a is equals to 0 means sk will be equals to just plus minus jb. So plus minus jb means the poles are basically, then in that case the poles are known as imaginary poles. So imaginary poles means if the pole they lie on the imaginary axis, then it is known as the imaginary pole. So for this imaginary pole also, similarly if you write the expression, so this will be the expression for gs. So gs will be equals to ak by s. So the value of a is now equals to 0. So in the denominator you will just have s minus jb and s plus jb. Similarly, if you take the inverse Laplace transform of this expression, you will get it is given by a term which is something like this. So that means it is purely oscillatory in response. It does not include any kind of damping, or there is no exponential term present in this term, so that the system there will be a damping in the system. So that means here this, if you plot this equation, you will see that there is, the system will have constant oscillation and it will keep on oscillating within the limits. These oscillations will neither increase nor decrease. So oscillations of constant magnitude will always be there in the system. So you can say that the output of the system is bounded for imaginary poles, but the impulse response, that is not absolutely integrable. So that means the system is marginally stable. So whenever you have a pole which is present on the imaginary axis, it can be in the at origin or it can be anywhere in the imaginary axis. So whenever you have poles like that, that kind of a system is always marginally stable and it will always have a perfectly oscillatory response, and the magnitude of that oscillation will remain constant throughout time. Now, so till now we have seen, like, if you have like single poles at different positions. Now the system might be so that you might have repeated a number of poles. So the system might be such that you have more or multiple poles at one position. Okay. So in case you have, let's say, if you have repeated real poles, so that means if you have r poles, repeated poles at s equals to minus a or s equals to a, then the impulse response will be modified and it will be given by an expression like this. Similarly, from here also you can find out if the value of a is less than 1, that is the poles they lie on the negative or on the left half of the S-plane, the system will be stable, and if they lie on the right half of the S-plane, the system will be unstable. And similarly, if you have repeated complex pole, then the expression or the impulse response expression changes and it becomes something like this, and so on and so forth. So the main thing that that we need to remember over here is that the presence of repeated poles on the imaginary axis, it actually makes the system unstable and the output becomes unbounded and it increases with time. So ideally we would not want any kind of repeated poles on the imaginary axis. Anyways, even if you have a single pole in the imaginary axis, then also your system becomes marginally stable. But the moment you have repeated poles on the imaginary axis, your system no longer remains marginally stable. It directly goes into the unstable region and the output becomes unbounded and it increases with time. So you can say that in general, so you can some general conclusions you can draw regarding the regarding stability. So these are so. In order to have, so let's say if the roots of the characteristic equation that you have, they have strictly negative real parts. Okay, so all the roots have a strictly negative real values. So in that case, their impulse response is bounded and the impulse response eventually decreases to 0. So that means you can say that the system is so this impulse response is absolutely integrable and the system is Bibo stable. If any, then the second one is that if any root of the characteristic equation has a positive real part or has repeated roots on the imaginary axis. In that case, the value of GT, that is the impulse response, that is unbounded, and it is not absolutely integrable and the system will become unstable. So if you have roots of the characteristic equation, which is equivalent to the number of to the poles of the system, if you have roots of the characteristic equation that lie on the positive or the right side of the S plane, or you have multiple roots on the imaginary axis, that means your system will be unstable. If you have one or more non-repeated roots on the imaginary axis, then the value of the impulse response is bounded, but it is not absolutely integrable. So you can say that the output, so if the input signal has a common pole on the imaginary axis, then the output becomes unbounded, and in absence of any kind of common pole, the output is bounded, but it has sustained oscillations and it is a marginally stable system. So depending on the pole position or the position of the roots of this characteristic equation, you can have an idea about whether you can have a preliminary idea about whether the system would be stable or not. Now, so from here you can say that if the poles they lie on the left half of the S plane, so that means that is known as the stable region. And whatever is there on, if anything lies on the right, any pole lie on the right half of the S plane, so that means that is the unstable region. And on the imaginary axis, if there is one pair of complex pole, then you have marginal stability. But if you have repeated roots, then it is unstable. Okay, so as of now we have only talked about like whether your systems are, if you have a bounded input to your system, if you are getting a bounded output, then we are saying that the system is stable, right? So what if let's say there is some condition which arises where your input itself is unbounded? Okay, so if you take an example of this ramp input or a parabolic input, so this ramp input itself is an unbounded signal because that is increasing with time, right? So that means whenever you're providing a system or the input to your system is an unbounded signal, so obviously the output of the system will also be unbounded. So in that case, can you say whether the system will be, can you just straight away say that your system will be unstable? So that is not the case. So we cannot, if you are dealing with an unbounded input, then even if the output is unbounded, you cannot straight away say that the system is unstable. So for that, we have to analyze the system in such with different kinds of mathematical tools which are available, that the stability can be found out depending on the position of the poles and zeros of the system. Depending on whether the poles and zeros are present on the left half plane or the right half plane, depending on that, you have to figure out whether your system will be stable or not, even though the input that is being provided to your system is an unbounded signal. Okay, so in tomorrow's class, we'll discuss about different methods which are there for determining the stability of a system. So do you have any doubts till now?
No, ma'am.
Okay, so then try to solve the problem that that is already there, and we'll discuss that in tomorrow's class, and then we'll continue with the lecture. Okay?
Yes.
Okay. Thank you, everyone.
Thank you.